So here's our lecture on section 4.1, extreme values of functions. Now, try that again. So first of all, let's define what we mean by extreme values. One kind of extreme value is called the absolute maximum value. Another extreme value is called the absolute minimum value. Now, these only happen when there is only one value and that is higher than any other value that a function produces. Now that value may occur multiple times, but there's one value, and we could say for all other values of the function, there is, for all other values of x, f of x is less than or equal to f of c. C is the location of the absolute maximum. F of c is the absolute maximum. So let's make sure we get those two ideas together. C is some value that kind of represents an x value. F of c is a maximum value if f of c is greater than or equal to every other value that the f function produces. By the way, not every function has an absolute maximum. The absolute minimum, that means that there's a place, c, such that the function whose value is f of c, that f of c is smaller than or equal to every other value that the f function produces. And not every function has an absolute minimum. So there's our working definitions. Next thing we need to do is talk about the calculus of this part of this information. You can still see some people writing down, so I'll let you finish what you're writing. I might even draw a picture. Maybe the sine curve. What if f of x is equal to sine?
I thought you meant like a fun picture while you were waiting for people to. No, I mean the sine curve isn't fun.
Okay. So what would we mean by the absolute value, the absolute maximum on the sine curve? 1. Okay. The absolute maximum is the value that the function produces. It never gets any higher than 1. The c values that might produce those, pi over 2, 3 pi over 2, so on and so forth. An absolute minimum? Negative 1? Sure. How about the standard parabola? Does it have it? Not every function has an absolute maximum. Is there some value that's on this function such that every other value is less than it?
No.
Nah. Okay, so that is standard parabola does not have an absolute maximum. What about the absolute minimum? 0. Because 0 is less than or equal to every other value on that function, or on that function group. All right. Okay. Here are some different ways that these absolute values can occur. An absolute value, an absolute maximum, like this one here, or an absolute minimum on this one, like that one there, can occur in the interior of a function. By the way, all of these drawings have something in common. They're all on a closed interval. We're not looking at all the values that x can take on from negative infinity to infinity. We're on some sort of restricted area of the x-axis. Okay, we're on an interval. We're on a closed interval in that we are including the endpoints. So this interval here is referred to as the open interval. interval written like this
Closed.
is a closed interval. So, on a closed interval, the function must have an absolute maximum and must have an absolute minimum. On a closed interval, every function has an absolute maximum and an absolute minimum. Now, one way that those absolute max and absolute minimums can occur is that they can occur in the interior of the function, somewhere inside of the interval from A to B. Another way that it can occur is that the maximum could be at one endpoint and the minimum may be on another endpoint. A third way that the absolute max and min can occur is that the max could be on the interior but the minimum on one of the endpoints. And the last way something can occur is that the minimum's on the interior and the max is on an endpoint. Those are the only ways maximums and absolute maximums and absolute minimums can occur on a closed interval. So if we were going on an absolute maximum hunt, where might we look? The endpoints is one place, and then the interior is the other place. But you know what? On the closed interval from A to B, how many different points are there? And then, so we really don't have time to look through the infinite number of interior points, do we? How many endpoints might they have? We have time to look at 2 endpoints, don't we? So let's say lesson number 1, if we're hunting for absolute maximums and absolute minimums, let's look at the endpoints. That's one place to look. When we want to look in the interior, let's look for more information that may help us find those interior absolute maximums or minimums, if they exist there. Let's figure out a way to find those absolute maximum minimums that may be in the interior. Well, to do that, I want to start looking at this other idea that's related to absolute maximums and minimums, and they're called local maximums and minimums. A local maximum occurs when the function reaches its highest, or that no nearby points are as high as the function is at that point. So here at x is equal to c, we say that there's a local maximum. F of c is the highest point with relationships to the points around it, to the values of the functions around it. Local minimums occur when we have some value of the function, and in the immediate vicinity around it, it is the lowest functional value. Now, local maxes and local mins maybe, they don't have to be, but maybe the absolute maximum or the min. For example, if we look at this point right here, the value of f of d is the highest point of that function in the immediate vicinity around d. But it also happens to be the largest value the function has on that entire interval from a to b. That point happens to be both a local maximum and an absolute maximum. Is this point right here, f of e, both a local maximum and an absolute, a local minimum and an absolute minimum? No, because there is a value smaller than that. Let's call it that local minimum. It's a candidate for absolute minimum. It's in the running. of all the infinite points from A to B, that location would be a candidate for absolute minimum. Let's say of all the infinite values that x can take on from A to B, this value C is a candidate for absolute maximum. So one way we can start looking at this question of where's the absolute maximum and where's the absolute minimum on a closed interval is to say, well, we know the endpoints are candidates. And of all the infinite points that are in the interior, the ones that have local maximums and local minimums, they seem to be candidates as well. Now, is there anything that jumps out at you about this local minimum and this local maximum? Something from the calculus standpoint. Something that has to do with derivatives, as the name of this chapter is, applications of derivatives. Ryan?
Those points have horizontal tangents.
Those 2 points have horizontal tangents. Is it easy to find out when a curve has a horizontal tangent? Sure. We find out it has a horizontal tangent by taking the first derivative and setting it equal to 0. You know, I also have this one circled in green. That one doesn't have a horizontal tangent. What's that?
It's on the corner.
It's got a corner or a cusp. It's pointy. Ouch. Okay.
Not differential.
And it happens to be an absolute max. It's a candidate for the absolute maximum prize, right? So maybe we have two things going on here. Maybe we have two things. Maybe the candidates in the interior are places that either have, as Ryan said, horizontal tangents, or the candidates are where there's no tangent, which another way of saying where the derivative does not exist. Maybe it's not maybe. Maybe is that's exactly what we're doing. Okay, so let's talk about local extreme values. If C is some interior point, some number that's on the inside the interval from A to B, we say that, first of all, f of C is a local maximum if f of C is greater than f of x for all those x's are right around C. If f of C is greater than or equal to f of x for values of x in some open interval that contains C. And that interval can be really small, as small as we need it to be. We say that a local minimum, f of C, is so if f of C is less than or equal to f of x for the values of x in an open interval around C. If we're talking about endpoints, we don't have to have an open interval around C. We only have to have a half open interval around C. What does that mean? So there's my drawing. Hey, I said there's a local maximum there at C. What does that mean? That if I create an interval around C, all the values of the function are lower than f of C. We're good there? What if I was down here at D? If I created an open interval around D, all the values of that function are greater than f of D. Would you call this point here a local maximum from an intuitive standpoint? Okay. Let's call that at B. And what does that mean by this definition, this very rigorous definition? If I had the closed interval, say half closed interval, where I included the B point, but then I went somewhere into the interior, and for all the values, all those values that the function gives on that interval, f of B is the tallest. is the biggest. A half-closed interval. Would you say down here at A, that's a local minimum? Sure. And so what kind of interval is this the smallest value on? Some half-closed interval from A to some open end.
Some resistant at past.
Can't go past C. Remember, these rules don't say how big the intervals have to be. They may be infinitesimally small. All right. So that's all the rigorous language having to do with local maximums and minimums. And here's the rule that's going to help us find those interior points. We say that f has a local max or local min at an interior point C, if that's true, and if f prime exists, that f prime function's got to be equal to 0. If we have a local max at C, and if f prime of C exists, f prime of C must be 0. If there's a local minimum at f of D, and f prime exists at D, then f prime of D must be 0. Let me tell you what this does not say. What this does not say is if f prime of C is equal to 0, f of C is either a local max or a local min. It does not say it. It says if it's a local min and the derivative exists, then the derivative is equal to 0. Why doesn't simply being a derivative equals 0 equate to a local max or a min? Well, can I draw a function like this? See, here's my axes. And I've got some function, I know, like the cubic function. Do you know what the derivative of that point is right there? It's 0. Is that a local max? It's a local min? No. So this doesn't say if I have a 0, I have a local max or min. What it says is if I have a local max or min, and if that derivative exists, that derivative must be 0. Places that have derivatives of zeros are good candidates for local maxes and mins. Local maxes and mins and endpoints are good candidates for absolute maxes and mins. Can I say that one more time more slowly? Places that have derivatives equal to 0 are good candidates for local maxes and mins. Places that are local maxes and mins and endpoints are good candidates for absolute maxes and mins. There's one other places where local maxes and mins can occur. And that's when the derivative doesn't exist, the corners or the cusps. We have a special name for the locations of horizontal tangents and places where the derivatives don't exist. And that's called a critical point. Any point on a curve that's in the domain of f, in which f prime is 0 or f prime doesn't exist. So we're not talking about a lack of derivative because of an infinite discontinuity, or because of a removable discontinuity. But a lack of derivative because the derivative doesn't exist. Those points are called critical points. And those critical points are great candidates for local maxes and mins. Now, I would have expected with the change from daylight savings time to standard time that everyone would have been caught up on their sleep. Danny? I would have thought that people would have been caught up on their sleep after getting the extra hour over the weekend.
Does that actually happen that you actually get an extra hour?
Yeah.
Well, you fall back, which means everyone turned their clock back an extra hour.
I just thought.
You lose it.
Yeah.
You lose the hour in
How does that work?
It just does.
because everyone agrees.
Yeah.
So it's actually 2:45 right now. And that's
How does 7 alarm clock on the same day? You just change time and not really.
It was weird because it happened 1:45.
Okay. So I have a question. Can we come up with a methodology for finding the absolute maxima and minima, or absolute maximum or the absolute minimum values of that function on that interval?
What is that?
That is
Two-thirds.
2/3. Well, let's go through a procedure that will always help us find the absolute maximum and the absolute minimum of a function on a closed interval. In fact, this methodology I'm going to show you is called the closed interval method. All right, where are the candidates? The candidates are critical points and endpoints. Right? So let's look at all the candidates. If you want to think of them as nominees, like for Academy Awards. And the nominees for absolute maximum are... Well, let's start with the critical points. What are the nominees based on their... the fact that... What is critical points again? The definition was they produce derivatives that were 0 or undefined. Well, I suppose we better start out by finding out, well, what's the derivative of this function? What is the derivative of 3 times x to the 2/3? 3 times 2/3 x to the what?
2x to the negative 1/3.
Negative 1/3? So 2x to the 1/3. Are there any values that, sorry, to the negative 1/3? 2 over root 3x is another way of saying that, I suppose, right? Are there any critical values? Are there any values that make that derivative either 0 or undefined? 0. Okay? So 0, comma, I write comma because it's critical point. So I need a point here. 0, comma, what happens when I put 0 into our original function? Or how about that? 0 f of 0, which is equal to 0, comma, 0, is a critical point. Are there any other nominees based on their critical pointness?
Endpoints.
What?
Endpoints.
Okay, endpoints aren't critical, but they are definitely candidates.
Yeah.
Are there no more critical points? Okay, how about the endpoints? What? Negative 1, comma. Okay, negative 1 comma f of negative 1. Let's find out what that f of negative 1 is. Negative 1 to the 2/3 power.
Agree.
If I take negative 1, I put it into here. I get negative 1 to the 2/3 power. Let's do the squared first. Positive 1, 1 to the 1/3 power. Still 1. 1 times 2.
3.
1 times 3. That's like a Monty Python sketch. Okay. So there's another location in which the absolute maximum or minimum may occur. Again, this is now we're working on the endpoints. And all right. And where's the other endpoint? 2 comma f of 2, which is 2 comma 2 squared is 4. Cube root of 4 is something that I don't know off the top of my head. I don't know what the cube root of 4 is. But Charlie's got his calculator. Charlie to the rescue.
2 cube root 4?
No.
Or just cube root 4? 1.5.
Okay, cube root of 4 is 1.58. Multiply that by 3 for me.
4.76.
4 point. Okay, I got 4.76 over here, and then what do you got? 4.76? 4.76. But we did 3 decimal places in this class? 2? Okay. So there are the candidates for absolute maximum mins. Who are our winners? Our envelope, please. The absolute minimum is 0. Remember, absolute minimum is the y value that came out. Remember when we said, what's the absolute maximum of the sine curve? You said 1. You didn't tell me what points it occurred at. You just said the highest value was 1. The absolute minimum is 0, and we found it right there. It was on the interior point. The absolute maximum is 4.762. You think so? All right.
Curve and we found the endpoints and we found the points where they intersected and then we found which one was the farthest.
Okay. Can we summarize the closed interval method? Take the interval, take the function, find its derivative, find out where the derivative is either 0 or undefined. Also find the value of the function, and find the value of the function at those critical points. Find the value of the function at the endpoints. Whichever is the highest of all those function values is the max. Whatever is the smallest is the min. Oops. I don't want that. I want this. Okay, your turn. Find the extreme values for the function f of x is equal to 1 over the square root of 9 minus x squared.
So does that mean it's an open interval?
Well, what I would think that means is that we're only interested in this function. Oh, is this function defined everywhere? Only between -3 and 3. So inherent in this problem is this is on the interval, the negative. Wait, is it a closed interval?
Doesn't it have to be?
Oh no, it would be.
If I put a -3 in here,
Yeah.
Yeah, that's.
I get a function that is
0.
0.
You can't have no zero.
So we're on that interval. So we're not going to be able to test the endpoints, are we? No. Okay, well let's see what we find out. Do a little exploration with your partners. You might want to start by finding out if there are any critical numbers. Critical points, I should say.
That's what kind of the derivative. Okay.
You start that process by taking the derivative. Yeah.
So this is 9 minus x squared over 2.
You're welcome.
Right.
Yes.
Would you guys check my derivative?
I think it should be positive.
No,
It's
I
positive.
got negative.
Because when you take the derivative, you do the bottom times the derivative of the top, which is 0, minus,
It should be positive.
so it should be negative 1/2 over 2 times.
Or if you just bring it up out of the denominator by giving it the negative exponent, still.
I was trying to be too tricky. I was trying to be too tricky. I am wrong.
Oh shoot, it was in the
That's probably the better way to put it. Okay. Are there any values of x that's going to make that derivative equal to 0?
Yeah, why is it?
Why are you doing the quotient?
Well, you could do the quotient rule.
Or you can just bring the denominator to the top.
I mean,
Negative one.
Did you see how I rewrote this using the negative 1/2 exponent?
Yeah.
And I think it's easier to use the power rule here.
Yeah, this is.
But if you use the quotient rule,
Because that's what my
If-
mind was.
Yeah.
if you use the quotient rule, you've got the bottom times the derivative of the top, which is 0, minus the top times the derivative of the bottom, and then this all over the bottom squared. Right?
Square.
So, well, it had a square root on it, and so when I square it, the square root goes away. When I take these two items with the same base but different exponent, what happens?
Subtract one from the.
I subtract one from the other. So this was a 1, and then I subtract a negative 1/2, and that gives me that 3 halves on the bottom. And then on the top, those negatives go away, that half and that 2 go away, and what's left is that x. So regardless of whether you use the quotient rule or the power rule, I think you get the same answer. At least I hope we do, because otherwise we are in deep doo-doo.
I just didn't see that it's not a good.
Okay. All right. So with my simplified version, are there any values of x that are going to make that derivative either undefined or equal to 0?
0, negative 3.
Okay, 0 makes the derivative 0, Negative 3 makes that derivative undefined, but that function doesn't exist at negative 3 either. 3 makes that derivative undefined, but the function doesn't exist at positive 3 either. So the only critical point is when x is equal to 0. So let's talk about, okay, so there's a critical point at x equals 0, and that critical point is 0, comma, 1/3. Okay, that's a candidate. A candidate for what? Local max or local min? And the ones that are local max and local min candidates are also candidates for absolute max and absolute min. Do we have any idea what's going on from there? I can graph it and see. You know what else I could do, Anthony? I could recognize that in this derivative, the bottom is always positive.
So it's gonna fall. It would be either or stuff.
What? Wait. When the interior of this expression is positive, I can take the square root of it and then cube it. When the interior of this expression is negative, the function doesn't exist. I'm outside that range outside of the negative 3 and the positive 3. This bottom is always positive in the real numbers. The only thing that's going to give the derivative a sign is in the numerator. This derivative is negative whenever x is negative. This derivative is positive whenever the x is positive. And this derivative is 0 whenever x is 0. So I have something that's negative, then 0, and then positive. I have a decreasing function that then has a horizontal asymptote, a horizontal tangent, and then an increasing function. What's my conclusion about what's going on right there then?
Absolute minimum?
It's got to be an absolute minimum. Anthony, yes?
I thought didn't you just say if x was negative, then y is negative?
I said when x is negative, f prime is negative. The derivative is negative. So whenever x is negative, the slope of the line must be negative, or the function must be decreasing. I say through this analysis that not only is 0 a local minimum, like Emily, I call it an absolute minimum. Are we good with that analysis? All right. Now, who actually graphed it? And what's your conclusion?
It's like 0 to me.
Okay. Looks like 0 is an absolute minimum to you as well.
Yes.
Wouldn't it be 1/3?
Sorry. The absolute minimum is at 0. The absolute minimum is 1/3. My language was off. Thank you for helping me. All right.
I'm going to have to work it all out.
No, we're just going to do this. What's the next slide? Oh, the next slide is number 10, which happens to be the assignment. Yeah. You may want to look at some more of the examples. They have some graphical examples in terms of finding maximum and minimums in the reading. I know that you guys are not used to reading math textbooks, but you might want to make an exception in this case. Right? All right. And I'm going to call this lecture to a close.